Welcome to the Deep Dive. Today we are diving into the world of microservices, and more specifically, how they manage data. We are looking at the database per service pattern, and this is something that powers giants like Amazon and Netflix. Have you ever wondered how these companies keep things running smoothly when they have millions of users hitting their services every second?
Absolutely. And when you're dealing with systems at that scale, efficient data handling isn't really optional. It's mission critical.
So let's imagine I'm building an online store,
Yeah.
not quite Amazon scale yet,
Yeah.
but a startup founder can dream right.
Yeah.
And I've got different services, for orders, customers, inventory, all the essentials. Each of these needs to store data. What's a good way to approach that without overcomplicating things?
Well, think about it like building a house, right? In the old days, you might just have one giant room for everything. But in a modern house, you've got specialized spaces, your kitchens, bedrooms, bathrooms, each one designed for its specific purpose. Database per service is kind of like applying that same logic to your online store.
So instead of one massive database that handles everything, we're giving each service its own room to work in. Okay? I can already see how that would make updates much smoother because if I need to remodel the kitchen, I don't have to shut down the entire house.
Exactly. That's the beauty of it. It's what we call loose coupling. So imagine that each part of your system is like a Lego block. You can swap them out, you can modify them without breaking the whole structure. And this agility is crucial when you're talking about companies that need to move fast.
Yeah, so instead of my order processing system crashing because the customer service team made a small database tweak.
Exactly. They can work independently, they can deploy updates at their own pace, no need to worry about bringing down the entire site with every change.
That's huge, especially in today's always-on online world. How does this actually work in practice, though? Is it as simple as just creating, separate database files?
Yeah. Well, it is a bit more nuanced than that. Think of it like this. There are different levels of separation you can achieve, and each one has its own trade-offs. So we can start with what's called private tables per service. Imagine a large apartment building where each service gets its own apartment. They still share the building's infrastructure.
So still some shared resources, but at least every service has its own dedicated space. Makes sense. What's the next level up in our apartment building in Albury?
All right, so moving up, we have what's called schema per service. Now imagine that each service has its own house, but they all reside on the same street. So they have a bit more independence than just separate rooms within a building. In database terms, each service gets its own database schema, which is like a logical container within a shared database server.
Okay, so even more separation. They could each paint their houses different colors without bothering their neighbors or anything?
Precisely. And this allows for more flexibility in terms of database design and even the types of databases used.
So if one service needs a really structured SQL database, but another one thrives on the flexibility of a NoSQL database.
They can each have what they need without any conflict. And then for the ultimate in separation, we have database server per service. This is like each service having its own private island.
No noisy neighbors to worry about at all.
Yeah.
That sounds like the ultimate freedom, but probably only necessary for very specific situations, right?
Exactly. Separate servers offer the highest level of isolation. And they're typically reserved for services that handle truly massive amounts of data, or maybe require very specific performance tuning that you just can't get any other way.
It's about choosing the right tool for the job. Speaking of which, our source mentions the FTGO application as a real-world example of this. What's special about their setup?
So FTGO uses that schema per service approach that we talked about. They opted for separate logical databases, but they all live on a shared MySQL server. It's a good middle ground that gives them flexibility without going overboard with completely separate servers.
Okay, so we've got these different ways to separate things out. But let's talk benefits for a second. Why would someone choose database per service in the first place? What are the big wins?
Well, besides the flexibility and isolation we've been talking about, a major advantage is agility. Teams can update their database structures or even switch to a completely different database technology if they need to. And they can do all of this without impacting other services.
It's like being able to renovate any room in your house without having to ask permission from the rest of the family.
Exactly. This independence is crucial for speed and innovation. Each team can move at their own pace using the tools that work best for them and their needs. But as with any architectural pattern, there are trade-offs to consider.
Okay, so let's talk downsides then. What happens when things get a little bit more complicated?
Sure. So one of the biggest challenges with database per service is how to handle transactions that span multiple services. Let's go back to your online store example. Imagine a customer is placing an order. That one action might involve updating the order database, decreasing the inventory count in another database, and maybe even adding a loyalty point in the customer database. How do we make sure all of those changes happen consistently when each of these services is like its own little island?
Yeah, that's a great point. It's easy to take for granted how a single database just kind of handles that for you. How do you even begin to coordinate something like that across multiple databases?
This is where things get really interesting. Those traditional transaction mechanisms that we rely on in a single database world, they don't quite translate to this distributed environment. In fact, the source material goes so far as to say that distributed transactions that touch multiple databases are best avoided, if at all possible.
Whoa, okay, red flag. Why is that? What makes distributed transactions so scary?
It really boils down to some of the fundamental principles of distributed systems. You might have heard of the CAP theorem. It basically states that in a distributed system, you can only guarantee 2 out of 3 desirable properties. Those properties are consistency, availability, and partition tolerance.
Okay, I'm vaguely familiar with those terms.
Mhm.
But remind me what they mean in this context.
Absolutely. So consistency means that everyone sees the same data at the same time. Availability means that the system is always up and running, even if there are some failures happening. And partition tolerance means that the system can keep working, even if communication between parts of the system gets interrupted, which happens in the real world.
Right, because networks are not perfect. So you can only pick 2 out of these 3. What's the usual compromise when it comes to databases?
So in many modern systems, especially at the scale that we're discussing here, availability is king. Think about it. Would you rather have a website be completely down because it can't guarantee that the data is perfectly consistent across all services? Or would you rather have it continue to operate even if some data might be slightly out of sync for a few milliseconds?
I think I'd rather have a website that actually works, even if it means like my order confirmation email might be slightly delayed.
Exactly. And that preference for availability leads us to some really clever patterns for handling these complex multi-step transactions. Our source specifically calls out the saga pattern as one way to manage this without relying on those rigid traditional transactions we talked about.
Okay, so the saga pattern, it's like a safety net
Mhm.
for when you have to update multiple databases. I'm adding that to my list to research later. It sounds fascinating.
It definitely is. It's essentially a way to orchestrate a sequence of smaller local transactions, and that way you can achieve the desired outcome even if something goes wrong along the way. But that's a deep dive for another time.
Agreed. Let's not get too sidetracked here. We've got more challenges to uncover. What else can make database per service a little bit tricky?
Another common hurdle is joining data across multiple services. Remember, each service only has direct access to its own database. So if you need to run a query that involves data from several services, it gets more complicated.
Right, it's like trying to assemble a puzzle, but the pieces are spread out in different rooms. How do you even begin to put that data back together again?
There are a couple of approaches, and our source mentions 2 in particular: API composition, and then there's CQRS, which stands for Command Query Responsibility Segregation.
Okay, CQRS. I can already tell this one is a bit more advanced, but I'm up for the challenge. Break it down for me.
All right, so let's start with API composition. The idea here is that instead of trying to join data at the database level, you handle it within the application logic. So if you needed to display customer information alongside their order history, you'd have a service that retrieves the customer data from the customer services database, and then it would make separate requests to the order service to fetch the order data.
Okay, so each service is responsible for fetching its own data, and then you assemble it all into a complete picture.
Precisely. This approach can be quite effective, especially if the amount of data involved is manageable.
That makes sense. What if we're dealing with massive data sets or like really complex queries? Wouldn't all that back and forth between services start to slow things down?
You're absolutely right. For those situations, CQRS can be a very powerful solution. It's a bit more involved, but the core idea is that you create separate data models for reading and writing data.
Wait, separate models for reading and writing. Now that is a brain twister. How does that help with performance?
It allows you to optimize each path independently. You can have a very high performance write model that handles all the updates and transactions, and then a separate read model that's designed specifically for fast retrieval and complex queries.
So it's like having a dedicated streamlined system for pulling up exactly what you need without bogging down the main database with all these different requests.
Exactly. One common technique within CQRS is to maintain what are called materialized views. These are essentially pre-joined data sets that are kept consistent with the source data. It's like having a continuously updated summary table that reflects data from multiple databases without having to run complex joins every single time.
Okay, I'm starting to see the appeal of CQRS, even if the implementation details seem a bit complex. It
Yeah,
sounds like it's all about finding these clever workarounds for the challenge of having these separate data silos.
you got it. And that's the key takeaway here. Data days per service offers amazing benefits in terms of agility, flexibility, and scalability. But it also introduces some new challenges that require careful consideration and often creative solutions.
So it's kind of like choosing the right tool for the job, right? You wouldn't use a hammer to cut a cake or a chainsaw to trim your bonsai tree.
Exactly. And as with any tool, understanding both the strengths and the limitations is essential to using it effectively. Database per service is a powerful approach, but it's not a magic bullet by any means.
Right. We've explored the core idea, looked at how companies are using it in the real world, weighed the pros and the cons. For our listeners out there, what would you say is the big takeaway? What should people be thinking about, especially if they are working with microservices?
I'd say the biggest takeaway is that database per service can really help you build more flexible and scalable systems. It allows teams to work independently, choose the database technologies that best fit their needs. But it also introduces some new challenges, particularly around managing distributed data and transactions.
It's like the classic no free lunch scenario. You gain some, you lose some. But hey, that's software development for you. Right?
Yeah.
There are always trade-offs.
Absolutely. The key is to be aware of those trade-offs and choose the approach that really aligns with your specific needs and constraints. There's no one-size-fits-all solution.
So for all the tech enthusiasts and curious minds out there, database per service is definitely something to keep on your radar. Even if you're not like knee-deep in microservices architecture right now, understanding these concepts gives you a glimpse into how modern applications are tackling the, ever-growing complexities of data management.
And it really highlights the fact that this field is constantly evolving. There are always new patterns to explore, new technologies to experiment with, and new challenges to solve.
That's the beauty of a deep dive like this. We're just scratching the surface. We've given you a taste of database per service, but it's up to you to decide if it's the right approach for your projects and if you want to explore it further.
And if you do choose to dive deeper, don't forget about those intriguing solutions we touched on. The Saga Pattern, CQRS. They're out there waiting to be explored.
That's right. Always more to learn and discover. And on that note, we've reached the end of our deep dive into database per service. We hope you enjoyed the journey as much as we have.
Until next time, keep those curious minds engaged and never stop exploring the fascinating world of software development.
And don't forget, you can now follow Code Impact Podcast on Apple Podcast, Amazon Music, Spotify, and other podcast networks. We'll see you on the next deep dive.